Welcome back. This screencast will talk about high-pass and low-pass filters mainly, but in order to talk about those in detail, we'll need to talk about complex impedance, and we're going to talk about this thing called the Bode plot, also known as the transfer function. So the Bode plot basically tells us, it gives us a plot of the gain versus frequency, and the phase versus frequency, and we'll talk more about those. First, a low-pass filter is simply it could be, this isn't the only way to make a low-pass filter, but probably the most simple low-pass filter is a resistor in series with a capacitor, where the capacitor is the second component. A high-pass filter is just the opposite. The capacitor comes first, and then the resistor. All right, so these very simple circuits can be analyzed in a complex way to give us lots of information, but not necessarily complicated, even though complex. In order to analyze high-pass and low-pass filters, we'll need to talk about complex impedance. So here's something in electronics. We don't use I to represent the imaginary number, square root of -1. We use J. That's because I is typically reserved for currents, and so as not to confuse imaginary number I with current, we use J. We'll also talk about, this is Ohm's law again with complex impedance, V equals IZ, and you see the modulus here, and that's because in order to calculate values that are going to be of interest, we're going to have to take the complex number and multiply it by its complex conjugate. All right, these will make more sense why we need to technically have this. But let's first talk about the complex impedance of a capacitor and an inductor, two reactive components as opposed to resistive. The complex, I guess should write down just R, just to let you know nothing too fishy is going on. Z of R, that's for the resistor, is purely real, all right, and it's just going to be R. Z of C, which is the impedance of a capacitor, is purely imaginary, and the complex impedance of an inductor is purely imaginary as well. What this means is these components are reactive. These actually, they don't burn up power, they just redirect it. All right, so that's a very fundamentally different kind of component. This component here, we spend energy into heat, and in this one we redirect signals either across or divert it to another part of the circuit. Okay, so the signals will reflect off here, or their phase will be changed in some way that redirects it. So it's as if these things impede. They do impede the signal flow or the current, but they don't spend it. Let's look at how these ones work as a function of frequency. So omega here is, let's write that down, that's the angular frequency. So omega is just equal to 2 pi f. All right, and we're talking about AC signals now. So f equals 0 would be a DC circuit, and f equals anything else, which is pretty much everything anybody's interested, is AC. So what we're interested in is what happens to ZC as omega goes up and omega goes down. So as omega, we'll see as omega goes up, we can see that the impedance of the capacitor is going to go down. Right, and that's just simply because we put a larger number on the bottom here, that thing is going to go down. So let's take a look at that. If you remember from last screencast when we talked about a capacitor, this thing, the picture is great. It's a block. You know, you have a wire coming here. There's the plate, and there's nothing connecting it in between. So if omega equals 0, let's look down here. If omega equals 0, this thing is infinite, an open circuit. Perfect. Okay. So what happens in the other extreme when omega is very high? When omega is very high, in fact, when omega is infinity, this thing looks like a wire. And sure enough, if you remember that the flow of current for a capacitor, it becomes greater and greater the quicker you change the voltage across it. And the quicker you change the voltage across it, that's related to the frequency going up. Okay, so imagine I go positive, negative volts, and then I flip the battery and I go negative, positive, positive, negative, negative, positive, positive, negative, negative, positive. The faster the voltage changes across this thing, the more current that flows through. Another way to look at that is that the more current flowing through this thing, the smaller the impedance is. All right, so you get that? Maybe we should write that down too. So let's see, omega goes up, ZC goes down. That's like IC is going up. Right, all those things are equivalent, and oppositely, as omega goes down, ZC goes up. And IC is going to go down. Let's box those. Okay, just with this simple information, we can figure out how a high-pass and a low-pass filter works if we make them out of R's and C's. And similarly, we can do this with R's and L's as well. Let's look at L in the same way. So as omega goes up, if we look at just from the equation here, as omega goes up, that means the faster that you're changing the voltage in the circuit, and it tells us that the impedance actually goes up. All right, and then we'll talk about this. So C, again, this is the capacitance. L is called the inductance. Remember, capacitors, they store electrical energy. Inductors, this is just solenoid, and this schematic is fantastic too. Inductors store magnetic energy. All right, and they actually work, you can see they work in opposition to a capacitor. There's no break, there's no open circuit. In fact, this is just a coiled wire. All right, so we would expect this opposite behavior. All right, so as omega goes up, ZL also goes up. All right, and that would mean that I would be going down. All right, and then as omega goes down, ZL goes down, and so that would mean IL, we'll just throw in an L there, IL is going up. All right, let's box those and then take a look at those. All right. So the way a solenoid works, if you remember from E&M, either 300 level E&M or 200 level E&M, is that the faster you try to change a current here, the more you have a back EMF against it. This is Faraday's law. And actually, there's an equation for that. We can write it down for the capacitor, too. You'll see how these are opposite. Remember, for the capacitor, we have IC is equal to C dV dt. Okay, I'm getting kind of crowded here, so let me box these. And in fact, maybe I should put a line in between these different components. All right. If you recall, for inductors, what we're interested in is V. V of L is actually going to be L di dt. All right, where L is the self-inductance of the solenoid of this little coil. All right, so solenoids, inductors, what they do is they resist flow. The faster you try to put something across it. So the faster you try to put current through this thing, the faster you change current, the more of a back EMF you get to oppose the voltage. All right, and so if we look at this as the frequency of the signal that we're putting in, again, omega is the frequency of the signal that we're putting on this thing or across this thing. As that goes faster and faster, as that change in voltage gets quicker and quicker, or the change in current rather, then the impedance goes up. This looks more and more like a huge resistor as omega goes up. And so that means that there's very little current flow. Oppositely, if omega is very, very low, then this thing doesn't look like a big resistor at all, and the current is big. All right, and so you can look at the limiting cases here. When omega is 0, look, that's just a wire. An inductor doesn't really do its job when omega is 0. It's very, very easy for current to flow across it. Armed with this knowledge, we can now take simple RC circuits that are set up in high-pass and low-pass filters pretty far, qualitatively, and then we're going to have to use some complex algebra to figure out analytically how they work. So here's what I'm doing now. If you can see, this is a voltage divider. This is nothing other than a voltage divider, except rather than putting in an R1 and an R2, it's a Z1 and a Z2. And that tells us that these components can be anything. They can be R's and C's, they could be C's and L's, they could be R's and L's, and so we're going to leave this now generic to component Z1 and Z2. So our equation for the voltage divider was V out was equal to V in R2 over R1 plus R2, but now it's just Z2 over Z1 plus Z2. And then there's something that's going to be more interesting to talk about, and that is, let's divide both sides by Vn, and we're actually going to get the ratio of V out over Vn, which is commonly known as the gain in electronics and other fields as well. Alright, so in these passive circuits here, the gain is always going to be at best 1. So at best in the voltage divider, as you know, if Z2 is a very stiff load, if Z2 is much, much bigger than Z1, V out will equal to Vn, and then the gain will be 1. In active circuits, where we're actually making amplifiers or other things, it could be that V out over Vn is more than 1. And certainly when you're designing an amplifier, you want it to be more than 1. But here the best we're going to get is 1, and we're going to get something small maybe for different frequencies that we drive the circuit with. Alright, so G is for gain, and as you can see, it's just Z2 over Z1 plus Z2. Let's take an example. Let's do it for the low-pass filter and see what we get using arguments of complex impedance for a capacitor and a resistor. Okay, so remember here our logic is when Z2 is much, much greater than Z1, then the behavior is that V out is equal to Vn. But when Z2 is less, when it starts getting to be equal and less than Z1, the voltage is going to go down. And in fact, when Z1 and Z2 are equal, it's half. All right, so let's put these. Let's just label this R, and we'll label this C. Okay, and so what we have is for the circuit over here, we have V out, the gain, over Vn is going to be equal to, so it's going to be, remember, C is going to be 1 over omega JL. Well, maybe we don't go that far. We'll just put ZC, and we'll put R plus ZC. I guess I could have put ZR. Let's go back and we'll actually do it to keep notation consistent. Okay, this is just plugging in R and C for subscripts. And here's what I want to say, and it's just above we had it written, I said it in words anyway, is that we know in this case that when ZC is much, much greater than ZR, then V out is equal to Vn. Okay, and then we also know that when ZC is much, much less than ZR, V out goes to 0. Okay, that would be, if this were R2, that the same thing would happen. And now here's the thing, when does that happen? So when C is really, really, really big compared to R, that would be for omega very, very small, for DC, all right? Remember, this circuit here, this looks huge, this impedance looks infinite at DC. So this one happens, the top one here happens for omega small, all right? And this one down here, see if there's not a lot of room, this one happens for omega big, all right? And then I'll circle those. So here's what we have. Now we have a circuit whose impedance changes with frequency, and in fact it's a voltage divider. And this voltage divider, we get what we put in when frequencies are low, and whoa, our gain goes way, way low when frequencies are high. And so if we were to sketch this, let me see if you can move these whole schematics up a bit. Let's move this sucker up. There we go. So if we could sketch this. Omega, and here's gain. We know that at low frequencies we're going to get a gain of 1, and then at high frequencies we get a gain of 0. So it's going to look something like this. All right, this is our guess, and we'll get more quantitative with it. But again, when ZC is much, much bigger than ZR, V out equals Vn. All right, and so this would be up here in 1. That's for low frequencies. And when ZC is much, much less than ZR, when does this thing look like more like a short? Well, it looks exactly like a short at infinity, but as we start getting smaller and smaller, the V out over Vn goes down. So that happens for high frequencies. So this is a low-pass filter. So low frequencies, Vn equals V out. because this thing looks so big, and at high frequencies this thing looks small, and you start loading the circuit, and the voltage over here starts tanking. In order to get more quantitative answers out of high-pass and low-pass filters, or any AC circuit for that matter, we need to actually look at complex algebra and look at this in more detail. So let's start by looking at this graph here, which maybe seems a little abstract, but hopefully this will clarify. Some of you maybe have done some complex algebra before. You don't need to have a math class. What I teach you in these screencasts and what we do on the board and lab and in our discussion will be plenty. So here's what we have. We have a y-axis, which represents the imaginary part of a complex number. Alright, so this y-axis represents the imaginary part, that's in purple. The x-axis represents the real part of a complex number, and that's in red. Alright, and then we can think of this as the length of the vector that is drawn from some point xy in the complex plane, so this was called the complex plane, is going to be represented by z. I'm using z because we're talking about impedance. Often people will say c, and this will be a plus b. So like usually the x will be represented by a and the y by b, or it'll be xy and then that number will be c. We're calling it z for impedance. So and typically when people talk about complex numbers in the complex plane, it's always the x-axis that is real and the y-axis that is imaginary. You might be saying to yourself or thinking to yourself right now, wait, I don't understand what an imaginary number means. Why would it have anything to do with anything real in electronics? You'll see it has something that is very, very real in electronics. You'll be doing complex algebra and getting very real measurable answers that correspond to imaginary parts of this complex impedance. Alright, one thing I don't have here is that a complex number, for example, this might be, if we look here, let's say that x is 20 and 20 ohms, the units are ohms, and y is 10, so the impedance then would be 10 ohms plus 20 ohms plus I times 10 ohms. Alright, maybe I should write that in. You would, for example, example, z could be equal to, and I'll still use my colors, 10 plus, oh, that's supposed to be a plus, let's erase that and make that a little better. 10 plus, not too much better, let's keep going, and then that will be 20, and the units on that thing would be ohms. Okay, and if you had a problem where you had numbers, I forgot my I there. Very important. Let's get the I on that 20 there. All right, it's a little bit muddled, but I'm just going to keep going. So 10 plus I times 20 ohms. This represents the imaginary part of the impedance, and this represents the real part, and the whole number is the complex impedance. Okay, so if I might shorten this and say RE later, but the real part of Z, when someone says the real part of a complex number like this, they mean the part that's not attached to the I. And when you say the imaginary part, you just mean the part that's attached to the I. One of the most common mistakes students make is they bring an I with when you say MZ. MZ is just whatever stuff is attached to the I, the coefficient. And in order to use this real Z equals X and this MZ equals Y, you need it in the format Z equals x plus I times something, alright? So this format here is one of the ways that people represent complex numbers. There's other notation, but if we're doing complex algebra, we always have to have all the real part added to all the imaginary part, and this is how we keep track of it. If you look, if we want to know the magnitude of the z, or any number for that matter, it's just the Pythagorean theorem, right? The length of this is going to be the hypotenuse, so it's just going to be x squared plus y squared. There's a more, or at least another significant way to represent that, and that would be z times z star. Alright, z star is the, let me label that as the complex conjugate. So this is complex conj. Okay, and if you see, as long as you can get a number in the format, but it must be in this format, as long as you get a number in the format of all the real part plus I times its imaginary part, the complex conjugate is simply changing the I to a minus. All right, and so if you see that, if you take this z times this z, you are going to get x squared plus y squared, and then taking the square root, you'll get x squared plus y squared, square root of which is the magnitude of any vector. All right. Last but not least, one of the things we're interested, if you look on this picture of the complex plane here, we might say, well, what's the angle between the x-axis and this vector? And it would just be the inverse tangent of y over x. All right, so I think these are pretty easy to see. It still might be abstract. Let me give you some words right now, and we'll keep going with this. We're going to be interested in what we'll show on the next slide is a complex gain. And what I'll want in order to actually get a gain that I can use in lab and measure is it's going to be the magnitude of the gain. All right, so the magnitude of gain, I need to use this idea of the complex conjugate times the complex number in order to get something like this is something I can use in lab. This is not. All right, but I need to know about the imaginary part in order to get the right answer. All right, same thing, the phase, what we're going to be interested is, so the gain is V out over V in, and I want the magnitude of V out over V in. I'm also going to be interested in the phase of V out over V in, and what that tells you is if you put a sine wave into a circuit, and you look at that sine wave you put in compared to what comes out, you want to see if they come out with any phase difference. All right, and that's it, and that's very important though. So you might put a sine wave into a circuit, and then you look at the input compared to the output, and they're right on top of each other, so that would be zero phase. There would be no phase lag or lead between them. However, what you might do is you might find that, oh, the one that comes out is shifted 90 degrees out of phase. And this can actually matter when delivering power to loads and circuits. Just as a note, I just realized that I put I's instead of J's, which we don't do in electronics. Let me see if I can erase those. Otherwise, oh, it's not erasing. So here's what we need to know is that what I should have done here is that my I's really should have gone to J's. And that's just in electronics. I might switch them in these screencasts or on the board because I'm used to a format like this. But in electronics, we want to do that. So change all my I's to J's, and then we'll be in the electronics format for complex notation. Actually, some people probably actually put I's in, but your book chooses to use J, and I think that's smart. So I'll try my best to keep that up. Okay, let's finish the screencast with an example of a low-pass filter. So low-pass filter, remember, we have R in series with C, where the V out we're looking at is across the cap. All right. If we flip components and we're looking at V out across the R, then that would be a high-pass filter. This is LPF, the abbreviation for low-pass filter. Remember, V out or V in, that's just the gain, and this would be this is your voltage divider. This is like Z2 over Z1 plus Z2, but our Z2 is C now. And then I've just filled in the components, the values. Oops, there's a mistake down there. Let's actually fix that one. That should be a 1 over. All right, do you see that? That's a 1 over down there that I kind of snuck in. Okay, so the complex gain in this case, the complex impedance is down here, but the complex gain in this case is going to be 1 over j omega c divided by r plus 1 over j omega c. All right, now that looks ugly already, so let's simplify that by multiplying the top and the bottom by j omega c. All right, and so what that will end up equaling to is you'll get a 1 on top, and we'll get a j omega rc on the bottom plus 1. So far, not too bad. All right, now here's a problem that we have. Remember, what we'll want in the end is to get things like magnitude and phase. This is our motivation, is we want to plot a graph of magnitude of g here versus frequency, and phase of this circuit versus frequency, and this is not in the format of real part plus imaginary part. So what we want is the following format. So we want, let's get the, we want our number to look like sum x plus, there I was careful with the j that time, plus y. We want that kind of format. Okay, that's the kind of format we want, but we don't have that. So there's a trick you do when you have, especially when you have a imaginary number on the denominator. And what we can do is we just multiply by the complex conjugate. I'm going to write this a little differently. So this is going to be, this might look a little silly, but you'll see why I'm doing it. I'm going to write this as 1. Let's back up. I don't want that. I'm just going to switch the order. 1 plus j omega RC, just to make it a little more obvious. So what I'm going to do is I'm going to multiply the top and the bottom by the complex conjugate, just so that I don't have an imaginary number on the bottom. And you'll see that this will help me get it in the format of like this. Alright, so it's going to be 1 minus j omega RC, and then on the top is going to be 1 minus j omega RC. When you get used to this, you'll see the whole point, the bottom's always going to be this squared plus this squared. Alright, that's actually the whole point of doing that. And then the top you might have to be a little more careful with. So what we have here is we're going to have 1 minus j omega RC divided by 1 plus omega RC squared. Okay? Very close. You might already see, can you already see the complex, or sorry, the real and the imaginary part here? Do you see the real part is just 1 over 1 plus omega RC squared, and then the imaginary part is a minus omega RC over 1 plus omega RC squared? We'll write that in detail on the next page, and then that'll be it for this screencast. Okay, so what we had from the last slide was that the complex gain, and I've added omega just to denote that it's a function of frequency. We don't have to, but g is a function of omega. We've been doing all of this work in the frequency domain. It's 1 minus j omega RC over 1 plus omega RC squared. What we're interested, if we want to measure the gain in lab, we can't get at this. We can't measure that directly. However, we can measure the magnitude of the gain. And the magnitude, remember, is just the length of that vector in the complex plane. It's the square root of the real part squared plus the imaginary part squared. Another way to do it, and this is how I'm going to do it right here, is just to take g of omega times its complex conjugate and square root it. Alright, this, I don't know if you can see it. If you look at this 1, if I kind of split it up over here, that's the real part. Alright, and then the imaginary, so the real part is 1 over 1 plus omega RC squared. And the imaginary part, we'll write this down later in the next slide, or this slide, is minus omega RC over 1 plus omega RC squared. Alright, so let's do it this way to get the magnitude of g. And that's just going to be, in our case, that's going to be equal to, so here's g, 1 minus j omega RC over 1 plus omega RC, oh, let's try that again, omega RC squared. Alright, that's g, and we're going to multiply it times its complex conjugate. So it's going to be, on the bottom is still 1 plus omega RC squared, and the top is what's different. It's going to be 1 plus. That's what makes the complex conjugate here. We just flip the sign on the j. Omega RC. Alright, and then in order to get it to be the right magnitude, we have to square root basically the sides of that triangle. Okay? I don't know if you can see it from here, but this is actually not such a hard one. On the bottom here is going to be 1 plus omega RC squared, and that whole thing is going to be squared. Let me erase this. That's a little sloppy there. Let's get a little better bracket on there. Okay. And then the top is just going to be 1 plus omega RC squared. We can already see that the top and bottom cancel out. Right, I'll just do it in a different color here. Can we see that this whole thing cancels out with one of those? And so what we're left with is we're left with 1 over the square root of 1 plus omega RC squared. Okay, cool. That's our result for the magnitude. Feel free to go back, rewind it, and slow it down if you have to. That may have been too fast for you, maybe it wasn't, but as you can see, the answer we get to is not very complicated, even though it is complex. Haha. Okay, let's quickly look at the phase. And again, this would be how much a sine wave of a certain frequency lags or leads the input that you put in. So on this low-pass filter, we're going to put in a sine wave, say of, I don't know, 1 kilohertz, and we want to see for that frequency, the sine wave that comes out compared to the original, is it ahead of the original or is it behind the original? And this is very real and something we can measure as well, and we want to measure. And so what we have again is that's just the inverse tangent of the imaginary part over the real part. The real part is just 1 over 1 plus omega RC squared, and the imaginary part is minus omega RC over that same thing. So the phase then is just going to be the arctan of minus omega RC over 1 plus omega RC squared divided by 1 over 1 plus, let's make that a little cleaner. Omega RC squared, and my bracket is getting really kind of sloppy and big there. But if you can see, the denominators cancel on this one, and what we're left with, if you can follow along with that sloppiness, is the inverse tangent of minus omega RC. Okay, and now I promise this is the last slide. These are the plots of the magnitude. I guess I should do this. I'm just realizing I should do that. There we go. This is the magnitude of the gain as a function of frequency, f. So again, omega is 2 pi times f, and typically in lab we measure f, we don't measure omega. But we could change it into omega if we wanted to. And here's the phase as a function of frequency. So this is for our low-pass filter. What this means is for low frequencies, there's a gain of 1, and those frequencies get through. But as we turn up the frequency, it starts to attenuate, and it goes to 0. All right, for the phase over here, what we do is we start with the output. The output sine wave that we put in at low frequencies is in phase with the input. So when we compare those two on an oscilloscope, they look like they're right on top of each other. However, as we go higher and higher in frequency, for this one, what we get is the output ends up leading. It comes early, basically. So what we have is the output we see gets ahead of the input. All right, it doesn't violate causality. It's not like the actual speed of the signal gets there, but compared to the input, the phase is negative. All right, and so that means that we have an early arrival of the output compared to the input. All right, these are called transfer functions. That's X is transfer, or Bode plots, and this is what you're supposed to do. You're supposed to at least probe regions of the Bode plot for your high pass and low pass filter as part of Lab 2. I'm going to give you one more screencast to talk about how you analyze these things. It'll be a really short one. There'll be one more to come. These are really nice to look at in a log-log scale. And I'm not showing these on a log-log scale. These are rough sketches of what they look like in linear units. And this is where 3dB comes from. Those are log units, and we'll talk about those in the next screencast. But F3D means corner frequency. It's basically where it turns the corner. And so this is a figure of merit that folks have just decided upon. Look, if I want to design a high-pass filter, I need to know where this thing turns the corner. If it's going to block the frequencies I want and pass the frequencies that I want. So in lab, you're going to be looking at regimes very much higher than the 3dB corner frequency. You're going to look at regimes lower. You're going to look at the phase to see what lags and what leads. And then it'll also ask you some questions, which I promise I'll answer, about things like, does it roll off 10 dB per decade? What the heck does that mean? And we need to know a little about the log scale and the log-log plot on this. But this is it. We did it for the low-pass filter. You could do it yourself for the high-pass filter. You could do it yourself for a different funky circuit. And just with a little complex algebra and the idea of complex impedance in the frequency domain, we can really, really get a good handle on how these circuits work.